Hello again and welcome to part 4 where we're looking at the Fluke 87V. When I first took this meter apart, I had pointed out that the shield was bent. And you can see this actually sits quite flat on the board. There's no real problem with it. But if you look at the video, it looked like what had happened was these tabs were not pushed down into the board. They were sitting up like this. And then the operator who had assembled the meter went ahead and tightened down the screws, so you ended up with something like this. So I was looking at the cover where these tabs fit through, and it doesn't appear that there's any clearance issues with this. So another member wrote me, and they provided me with pictures of a slightly older Fluke 87V than this one. And they were quite surprised after seeing my video, and apparently they took theirs apart. And sure enough, as soon as they slid out the circuit board, they realized that their shield was bent up as well. And their meter has the same shield as this one. It's the exact same profile. So what we're going to do is put this meter back together, and let's just see if there's any reason at all why that shield is getting bent. And so I've gone ahead and tightened this down, and you can see it fits reasonably flat. You know, there's a little slot in the side of the board right here. So this lip fits right down inside of there real nice. So I'm not sure what the problem is. It looks like this is how it's meant to be put in. Again, I can't really see what would cause that other than possibly sloppy workmanship. But the fact that this other user's meter was the same way, that's pretty discouraging because his meter is about 2 years older than this one. And again, this meter came straight from Fluke. So, yeah, so I don't have an answer for why that was like that. So one of the concerns was how close the shield is to the high voltage areas. All the high voltage is basically going to be in this area. The MOVs are right here, and you can see the shield's got a fair amount of cutout. This area here, this is the common point. You know, we do have the fuse and the shunt, but you can see I've got this pretty good slit sitting across them. And the shunt going back to the common point is sitting across here. So I don't see it ever arcing from here up to the shield. That's not going to happen. Our second current input is right here. And of course there's a fuse across these 2 points. But again, you've got this nice slit cut in here, so I don't see any way for it to arc from here to here. On the far left side, this is our normal volt ohm input. And again, we have the PTC sitting here and our high voltage resistors up in this area. And then our MOVs are right in this area here. In the picture that the person had sent me, it looked like the shield was bent down. But even if that's the case, boy, you'd really have to bend this over, and I still don't know if you could get it to arc between any of these pins going back to the shield. So I don't see any problems with that. I'll tell you, the one thing that does kind of concern me though is having this cable with this kind of sheathing here wired in right below the fuse. I'm not sure what voltage this is good for. Alright, so I have my ESD gun out, and again I can use this as a variable power supply. So we're looking at the IEC 61010-2, and in this section here we're talking about the fuse inputs. And again, we're replacing this with an open circuited fuse. We're applying a voltage that is 2 times the highest rated voltage for any terminal, and that's applied to the overcurrent protected measuring circuit for 1 minute. Source of the test voltage shall be capable of delivering 500 VA. Again, of course, this power supply can't even come close to that. But I am looking for any kind of a breakdown to occur. What I've done is I've taken a safety fuse and I've blown this open. So we've marked it test. I'll just use this going forward. And let's just start with this circuit here. And for this test, I'm going to leave the battery in place, because again, this meter is rated for 1000 volts. We're going to be applying a 2000 volt signal. I think what's happening is the circuitry that's used to detect if the leads are in their right position is actually clamping this input voltage. Whatever's dragging this power supply down, I can't overcome it. So the best we're going to be able to do, it looks like, is to test it at about 1.36 kV or so. Let's see where it folds over, right about there. So about 1.3 kV. Alright, let's just let it set. Alright, at least it survives that. Unfortunately, our test fuse is a little longer than the 400 milliamp one. You can see there's definitely a difference in the length. So we'll have to test this one with no fuse. Again, I'd like to see 2 kV out of this power supply. Yep, does the same thing here. Just again let it set at roughly 1.3 kV. Alright, that looks fine. Okay, so I could smell this thing heating up when I was testing it. And if you look right here, you can see this resistor here is discolored just slightly. So both of these are 1 meg resistors, and these are used for part of that lead detection circuit. And basically this is what's getting hot. This is the reason that I can't supply the voltage, is we're basically drawing down this power supply too much with these resistors. So you look at it and you say, well, it's a 1 meg resistor, but at 1.3 kV, these resistors are going to be dissipating 1.69 watts. If I could put out 2 kV, these will be dissipating 4 watts out of these packages. Now, of course, that's only going to be for 1 minute is what the test calls for. I assume it's fine, or the meter wouldn't have been certified. I am sort of amazed that they're not using a higher value than this. I tell you, I'd like to pull that resistor out and then repeat the test, because I'm still concerned about it breaking down through this sheath into this wiring here. But again, I just don't have a way to conduct that test right now. I'd need a bigger power supply than what I have available. Alright, to simulate our 1 mega ohm resistors, I have here a couple of parts from KDAC. These are part number TG950. These are 2 mega ohms each. And you can see, if we check these with our Ryman on the left, so basically 1 mega ohm. So I'm going to be testing out a different power supply to conduct this test. You can see it's made by applied kilovolts. To put 2000 volts across a 1 mega ohm resistor, we need 2 milliamps. And again, we could only achieve about 1.3 milliamps with our gun. Basically, I have these high voltage probes here attached to this attenuator. And again, this attenuator is a divide by 10. This attenuator has multiple HRC fuses included in it and several high voltage resistors, and then it's all potted. So I use this to make high voltage measurements like we're about to do. We should be able to get 200 volts on this meter, and again, that'll equate to 2000 volts across our 1 mega ohm resistor. And there you go. So 200 volts, and again, I can turn this up a little bit. There's 2060. So that's pretty much spot on 2 kV. Let's get our meter set up and try to repeat this test one more time. Again, we'll be starting with our 10 amp input. You can see I have my test fuse installed. Again, we'll be applying 2 kV for 1 minute as per the IEC standard. So here we go. So you can see the power supply kicked out immediately. Alright, I can't get the meter in the picture. Right now I'm basically at 0 volts. I'm going to go ahead and start turning it up. It's 270. There's 1,000 volts. There's 1,400. $1,500, $1,600, it definitely looks like it's arcing right inside of the fuse. So all I've done is just remove the fuse. I can't really tell if this was arcing from this down to our wire underneath or if it's actually arcing inside of the fuse. So let's just try to run it without the fuse. Looks like just the fuse body itself is what's breaking down. It's at 2,060 volts. You have to be fairly careful when you're playing with power supplies like this. I don't know if you can see the smoke coming out of the meter right now. You can definitely smell it. Again, the majority of that heat is going to be right off of this resistor. Let's try it in the other current input. Again, the same test, and we'll enable it for another 1 minute. I don't know if you can see the smoke coming off of that meter now or not. And there you go, there's 1 minute. Doesn't look like there's any damage to the resistors or to the circuit board. Everything looks fine. Alright, so I cut open our little safety fuse. I emptied out the sand. Essentially, I cleaned out what was left of the element. When I blew this fuse, I did not do it with a very high energy source. I just kind of crept up on it until the fuse popped. So what I'm going to do is put a little piece of heat shrink over this. Alright, let's go ahead and turn it on. There you go. So yeah, it was just arcing inside of the fuse. And again, even with the fuse in place now, it doesn't seem to arc through to the 9-volt battery cable. That's really what I was interested in knowing. Yeah, it looks good. Alright, I went through a full functional test except for the current input, and the meter seems just fine. So the first thing I want to do is make sure that the lead detection circuit isn't damaged. And you can see that one definitely works. Let's try this one. So no problems there. So let's just go ahead and we'll switch this over to microamps. Alright, so you can see we're in the microamp scale, and it's reading 4.565 milliamps. Very close to what the Bryman reads, so no problems there. Let's go ahead and turn it to the milliamp setting and select DC. You can see the 2 meters are basically reading the same thing. Let's go ahead and turn the current up a little bit. That looks fine. Let's try the amps input. You can see both meters read the same value just fine. Turn it up a little bit higher. That's about the limit of this power supply. Yeah, it looks like no damage to the meter at all. So I'd say it passed that test just fine. Again, that little bit of smoke we're seeing is just off of those resistors. If you run it there long enough, I would assume that the resistors would probably fail. Again, at 2000 volts at 1 meg, we're dissipating roughly 4 watts out of that package. So it's a fair amount of power. Alright, so the next thing we're going to be doing is our AC line test. Before we do that, I functionally tested the meter, and I took a couple of measurements. In the continuity mode, this meter reads an open circuit voltage of 2.653 volts. The short circuit current is 1.0032 milliamps. With a 50% duty cycle waveform, the point where the meter starts to miss is at about 2.6 hertz. The minimum pulse width that I can detect with this meter is somewhere around 500 microseconds. It seems to start to really skip at about 300. The short circuit resistance that it detects is 44 ohms, and where it releases again or goes open is 94 ohms. So if I turn on our meter, and I'll go ahead and enable the output, and you can see the AC voltage is roughly 116 volts, and the DC component is 237. What I'm going to do is just go ahead and rotate the knob through all of its settings, and then we'll functionally test it and make sure we didn't damage the meter. And again, this generator will limit the output current to, I think, about 40 milliamps where I have it set right now. So if the meter draws more current than that, the output will be disabled. Alright, so I went through and I functionally tested the Fluke 87V, and it survived that test just fine. So, the person that had sent me the information about the shield had asked another question about this particular meter. They were asking if the meter was in the high Z mode, so it was in the millivolt range, and you overrange the meter, what they say happens with their meter is it'll overrange and then it'll never clear out. So let's just try that in normal mode. What I'm going to do is apply a 5-volt signal to the input of the meter. It should overrange, which it does. I'm going to remove the voltage. It should return to 0. And the question is, if I do this in the high Z mode, will it return to 0? So again, I'm going to apply a 5-volt signal. You can see it overranges, and now I'm going to take away our 5-volt signal. No problem, it returns to 0. I went back and ran the same test on the older Fluke 87V that I showed earlier, and if you overrange that meter on the high Z mode, it will latch. If I short the leads together, it'll clear the overrange. Likewise, if I rotate the knob off of the millivolt range, that'll clear it as well. So I wrote 2 friends of mine that also have Fluke 87Vs. One of them was a firmware version 3.01, and its serial number starts out with 1057. That meter behaved the same as the older Fluke that I had here. I also talked to another friend of mine that has a firmware version 3.03, just like this one. That one is a serial number 2842. And again, that meter latches, and it will also clear when you short the leads as well as when you rotate the knob. So I believe that that was just a design flaw with the earlier meters and something that's been corrected in this latest version. So before I had built my ESD gun, I used to test all the meters using this piezo or piezo grill starter as I call it. And I damaged quite a few meters with this. And a lot of people were concerned that the output off of this was just too much for the meters to bear. And it was for quite a few. But I went ahead and I tested this against the IEC standard, and I showed the waveforms off of this, and basically this thing puts out essentially nothing. When I started running these tests, people were saying, oh, this is all dangerous, and thousands of volts, you could get killed instantly. And I was pointing out that this grill starter here puts out in excess of a couple of kV, no problem. And I could take this all day long right across my fingers, and I'm not going to die from that because it just doesn't have the energy. Of course, this generator can put out about 20 joules in excess of 5 kV, and that could be lethal. Now, this generator up on top, when you start playing with this, you better have a healthy respect for it. Again, it's a short pulse. It's only a half cycle of an AC line, but there's a fair amount of energy behind that pulse. So you have to be kind of careful with this stuff. Anyway, so I thought what I would do is static test the front end of this meter using this little grill starter like I had in the past. Again, I'm not expecting this to have any effect on this meter whatsoever. When I previously looked at the 87Vs, I had never exposed those to my AC line test or the ESD testing. So let's just go ahead and give this a try. Again, we're going to be applying 5 pulses, both positive and negative, in each mode of the meter, and these will be a direct discharge. That's it. So let's go ahead and now functional test the meter. I think we can get an idea real quick. Let's just see if the resistance works. Normally, if the input were damaged, this thing would leak and you would start seeing a resistance even without the leads installed. So this is a 10 Mega Ohm resistor. That looks fine. Of course, let's just try it in capacitance mode. This will be a 0.1 microfarad. That looks fine. This will be Diode Check. Looks good. And let's just try it in our millivolt mode. So this should be about 40 millivolts. Looks fine. And let's just try our temperature. Again, this should be about 500 degrees Celsius. That looks fine. This will be our 5 volt signal. And that's fine. And for AC, this will be 2.5. Yeah, so I'll go ahead and finish testing the meter, but it looks like it's okay. You can see I have our new ESD gun out. Again, this gun closely follows the IEC standards. It'll output roughly a 15 amp peak in about 800 picoseconds. And again, we're going to be applying 5 pulses to each mode of the meter, both positive and negative, and then we'll functional test it. Alright, again, let's just do a real quick check. Should be roughly 2.5 volts. This should be roughly 70 volts. That looks fine. Should be around 60. That looks fine. That should be 5 volts. That looks fine. It should be 2.5. That looks fine. Again, 2.5 here. That looks fine. This should be roughly 40 millivolts. That looks fine. This should be a little over 1,000 degrees. That's fine. This should be roughly 500. Looks good. And this should be room temp. That looks fine as well. Again, this is with the leads open. Let's just try it with a 10 meg resistor. Looks good. This will be a 0.1 microfarad capacitor. That looks fine. I'm sure the continuity test works fine. Let's try Diode Check. Yep, that looks fine too. So I'll go ahead and finish functional testing the meter, but it looks like it survived the ESD gun just fine. Alright, you can see our scope is at 500 volts per division and 100 microseconds per division. And we're 2 divisions up, or 1000 volts, with a 100 microsecond full width half height. And you can see our high voltage probe, and again I'll just be looking straight across our meter. Again, this transient generator will put out a maximum of about 20 joules. This is not a safety test. I'm really only considering the robustness of the meter. We'll be applying 5 transients, both positive and negative. Alright, let's go ahead. Alright, that's it. Let's go ahead and turn on the AC output. You can see it's reading roughly 120 volts. That's normal. Let's try it in DC. And you can see we're at 240 volts roughly. That's normal. Alright, this should be roughly 40 millivolts. That seems fine. Let's just try temperature again. This should be roughly 500 degrees Celsius. That seems fine. Again, normally when the meter's been damaged, it'll read some low resistance. You can see with leads open. That's just fine. This will be a 10 Mega Ohm Resistor. That seems fine. Let's try it with a 50. That looks good. Let's just try capacitance real quick. So this will be a 0.1 microfarad. That seems fine. And of course the diode check I'm sure is fine. Yep. So I'll go back and finish functional testing this. Alright, the meter passes functional just fine. This is pretty much what I would expect from this meter. Again, the previous one that I'd looked at failed at 1.5 kV. So I think that's going to be it for this video. Stay tuned for the next segment where we finish transient testing it, and then maybe we can start our life cycle testing. So we'll see you in part 5. Later.